Assalamu alaikum. My name is Abdul Mukeet, the student of Masters in Structural Engineering from BZU. I'm starting presentation for my thesis. Bismillahirrahmanirrahim. My topic for the thesis is behavior analysis of high-rise buildings with shear wall at varying locations across different seismic zones. So before starting the actual analysis and the data for discussion, a brief introduction and the history for this one. Since the high-rise buildings support dense urban areas where land is limited. High-rise buildings are increasing day by day, so there is a use of make them structurally stable so that they can resist more lateral loads such as wind and earthquake loads. And as per BCP, Building Code of Pakistan, uh, adequate lateral load resisting system should be essential for earthquake resisting structures. If we talk about the history, like in the past 2005 Kashmir earthquake and 2013 Balochistan earthquake, there were too much destruction for the poorly detailed structures. So damage was identified by inadequate seismic detailing and weak lateral load resisting systems. So now for the modern high-rise buildings, there is a require of such systems like shear walls, bracing, and base isolation so that lateral loads can be resisted properly, transferred to the foundation, and their effects and their patterns we will discuss in the next slides. Now talking about the other systems like shear wall is the most efficient lateral load resisting elements in the high-rise buildings. They increase structural stiffness, strength, and seismic resistance. They reduce lateral displacement, interstory drift, and improving overall building performance against these earthquake loads, lateral loads. So, problem statement for my thesis is this research address the critical need to identify the most effective shear wall placement to minimize the structural vulnerability in high-rise buildings across different seismic zones. Now, the objectives, there are three objectives actually. Initially, we will discuss the placement of shear wall, how they behave, how they react. Then there will be a comparison between all the shear walls in different seismic zone, and then there will be a practical recommendation for the shear wall location after analyzing all the data. If we talk about the shear wall is is a structure from foundation to the top of the building and transfer the load to the foundation safely so that there should not be any localized stresses and all the stresses and this can be transferred to the foundation equally and in proper way so that there should not be potential structure failure. If we talk about the seismic zones in Pakistan, Pakistan seismic zones as per the Pakistan Building Code divided into four seismic zones, for zone 1 to zone 4. So 1 is the least expected zone hazard and 4 is the highest seismic zone. So in this thesis, we will analyze two zones actually, zone 3 and zone 4 only to have good results. This is the chart which is showing all the patterns. Zone 1, Zone 2 is divided in two parts, 2A and 2B, Zone 3 and Zone 4. Now, if we go about the research methodology, these are the steps which we followed. Firstly, we define the building geometry and materials, then define load combinations, ELF, RSA, equivalent load force, and response spectrum analysis. Set seismic zone parameters for zone 3 and zone 4, and then we run the analysis and extract results for all the parameters like displacement, drift ratio, overall drift, shear, acceleration, stiffness, like this. And then the analysis of the results will be shared. So if we come to our model, model was defined as a 10-story reinforced building with the rectangular plan, 140 feet into 100 feet as shown in the photo below. So all the grids are uniformly distributed in 20 feet grid in X and Y direction. Story height is uniform because for the comparison purpose, it will be uniform. 11 feet and total height will be 110 feet. Column size as mentioned 30 into 30 inch, beam 15 into 24. And rigid diaphragm was adopted for uniform load force distribution. So these are the three combinations which we will be discussing in the later slides. Like first one is the core shear wall. Second one will be the edge shear wall. Third one will be the corner shear wall. This plan from the ETAB models. So total of 12 analyses we will be performing for comparative seismic analysis, and this all will be for these three combination of core shear walls, as we discussed in the previous slides, in two zones of Pakistan, zone 3 and zone 4, and two analysis method, equivalent lateral force method and response spectrum analysis. So all this combination will give us like this 12 combinations to do the analysis, as firstly are in the zone 3 for ELF, then next three are for RSA zone 3, then for zone 4 ELF, and then zone 4 RSA. Total of 12 structures we will be discussing now. Now for the ETABS model, firstly for the equivalent lateral force ELF method, like for the brief description for this one, introduction. ELF is a simplified static method for estimating seismic load forces. Base shear is calculated using CA, which is the acceleration coefficient, CV, velocity coefficient, structural weight, importance factor for this type of building. To have analysis point of view, we have taken one, and response modification factor, which is from 3.5 to 8.5. So we're taking as a 8.5 for this one. Forces are distributed to stories according to the height and mass, and 5% accidental eccentricity is included to account for torsional effects. So below are the screenshots from the ETABs having all the values like it is showing for firstly for the X direction for zone 3, soil type SD, all the values like this, eccentricity ratio 5%, overstrength factor 8.5, importance factor 1. So second one is for the Y direction, same for zone 3, and then X direction for zone 4, and then Y direction for zone 4. And then we have load case data for EQX and EQY. And then we'll go for the other definition of response spectrum analysis, RSA. RSA is a dynamic analysis method based on model response of the structure like vibration and CQS, CQC, such kind of patterns which ETAB is using. So calculating the natural frequencies and mode shapes are evaluated for seismic response. As per UBC 97 response spectrum parameters, same values for CA and CB will be applied to have a consistency and to compare the values. And model combination using the complete quadratic combination CQC method to handle closely spaced modes as generated by the model inside, and directional combination using square root of sum of squares to incorporate multi-directional effects. Apart from that, 5% model damping and 5% accidental eccentricity are included, and RSA is a more realistic picture for building performance under the actual dynamic loading condition, as it is considering all the uh, time and acceleration and model analysis. And also the orthogonal effect is considered at 33% of perpendicular direction. It is not considering just in the one direction. That is why it is giving a realistic approach of the model analysis. So, to put the values of RSA in the system, the same for the zone 4, same values of CA and CV. And for zone 3, this is generated, and then we'll come to load cases. So three mods are generated here, U1, U2, U3, with the same CQC pattern as per the software. And then we'll go for mass source and load pattern configuration. Load pattern will be calculated as dead load we are taking as 1 and live load 0.25, reduced live load for the mass source. Applied force are used to calculate the mass distribution within the structure. Load pattern application is vital to accurately modeling for the seismic response of the building under equivalent load and response spectrum analysis. So this is the factors we are using to uh, equally distribute the load in both analysis for an analysis of both ELF and RSA. Now for the seismic zone parameters, as we discussed earlier, zone 3 and zone 4 will be used as per UBC and BCP seismic parameters. CA, as I highlighted before, present acceleration coefficient, and CV presents velocity coefficient. Soil type for generic point of view, we have chosen the same SD stiff soil, exposure type B, so that all the parameters will be same while analyzing the different combinations. And seismic parameters directly influence both ELF and RSA results by altering. So like we will discuss now for the base shear, acceleration, model properties, and stiffness, each and everything in the next slides. These are the values which we are choosing. Now for the results and discussion. After analyzing 12 models, we have different charts. So if we talk about the diaphragm center of mass or maximum story displacement, like first chart is showing for zone 4 and zone 3, core wall in EQX. So this is general representation, like zone 4 is always showing more displacement. So this blue is showing more displacement than zone 3. So this will be a like general everywhere almost. Zone 4 will be showing more critical values than zone 3. If we go to the second chart, comparison of corner shear wall in zone 3 and zone 4. Again, zone 4 is showing more displacement. If we go to this one, again, we can see this blue line, zone 4 is showing more displacement. For this one, zone 3 and zone 4 core wall in RS direct analysis, still it is showing the same. Zone 4 is showing more displacement. For this one, same zone 4 is showing more. For edge wall in RSX, blue line is showing more displacement. So these are all the combinations we have generated. I will explain briefly for this one. Like for example, in as per our analysis, we understand like corner wall is showing very less displacement. So whenever we will compare the corner wall with the other walls, like for example, this one corner wall, green line, this is showing less displacement. Okay. So even in zone 4, if we compare two walls, corner wall and CNW. So corner wall is still showing less displacement. Like this, if we compare all the zones, so this zone 4 CNW RSX and zone 4 CNW EQX, it is showing less displacement. So these are all the combinations which we compared with different zones with different uh, core walls. So everywhere, like in a general, we can say it is showing corner wall is showing less displacement. If we go to the next slide, all are comparison like this is the zone 4, zone 3 core wall. So in EQY direction, zone 4 is showing more displacement, zone 3 is showing less displacement. So for example, randomly if we pick any chart, like for example this one, zone 3 and zone 4, again zone 4 is showing more displacement. So these are all the combinations. Here also we have zone 4, all the EQX, EQY, and response spectrum. So this one zone 4 corner wall, EQY showing the less displacement. So overall we can say like in comparison of zone 3 and zone 4 obviously has more displacement. And if we are comparison in uh, shear walls, so the corner wall is best suited in the mass displacement. It has a very less displacement in overall comparison of all the shear wall placement. Now, if we talk about diaphragm drift ratios, diaphragm drift ratio is having the same concept as of diaphragm mass displacement, because it is a relative movement between the floors. So just in the start, if we compare just the zones, for example, core wall, so zone 4 is showing more drift and zone 3 is showing less drift. So like this, zone 4, zone 3 for all the walls we compare here. Later on, when we are comparing with the different analysis method, for example, if we come here, so again we can see like zone 4 corner wall. Corner wall is showing less drift than the core wall and also the edge wall. So in this case, also corner wall is showing more stable response in diaphragm drift ratios. If we go to the next slide, the same if we compare like for example zone 4 in all ELF and RS method, still if we can see this green line, zone 4 corner wall RSX is showing the less drift, and all other are showing for example this blue line, zone 4 core wall is not showing that much stiff response, having more displacement, so that is why it has more drift ratios. For the next chart, if we explain this one, uh, then this blue line Z3 corner wall. Again, the corner wall is showing the low drift ratio. And randomly, we can check all the charts. So in we will discuss this all this calculation in the later slides. So these are all the charts. Randomly, we can discuss this one. Now for the story drift. Story drift is also the same response as of drift ratios. So again, we can see like in comparison to zone 3 and zone 4. Zone 3 has less drift, and zone 4 has more drift. Now we'll go and discuss these issues, these patterns in the next slides. If we compare like zone 4, for example, here, in all the walls, still we can see like corner wall is showing less drift. So in this case, also in the drift calculation, corner wall is showing more good response. And obviously, when there will be less displacement, less drift, then the stresses will be more. This we will discuss in the next slides. So again, this story drift, all the combinations are here. We can discuss in the next slide. For example, if we compare all the walls here in EQX, EQY, and RSY direction, still we can see like corner wall is showing less drift for this green chart line. Then we discuss story shear. So story shear is inversely proportional to our displacement actually. So before, as we were discussing, corner wall has less displacement, then corner wall in this case will be have more shear and ultimately more uh, moment in the base. So again, in the start, as we have compared the zones, we can see like zone 4 has more shear, zone 3 has less shear. We will go to the next slide uh, to cover this one. For example, now if here we are comparing zone 4 with all the three walls in EQS X analysis, so we can see this C and W has more shear now, less displacement, more shear. Now we will quickly go to the next chart. For example, here zone 3, again we can see like C and W, this blue color line, Z3, this one will be have more shear. This all the analysis we will discuss one by one in the next slides. Now we'll go to the next part, overturning moment. As I discussed, like for the corner wall is more stiff, more less displacement, so it will have more shear and more overturning moment. So here we can see here C and W in response spectrum, it is giving the maximum shear 315, and the core wall is giving the minimum shear here, core wall EQX 196. And also in the X direction, uh, here it is more corner wall RSY 245 and core wall EQY 195. Now we'll talk about story stiffness. So story stiffness, because of less displacement and most efficient behavior of corner wall. So story stiffness of corner wall will be more than all other. Like for example, if we are comparing here for zone 4 corner wall, red color line, this is showing more stiffness. Here also like blue color line for this, if we are comparing for zone 4 in Y direction, again we have more stiffness in corner wall. So if we talk about story acceleration, like for example, for the corner wall, if the displacement is more, story acceleration will be less. So like here, if we are comparing for all the zone 4, 3, for all the walls, core wall, corner wall, and edge wall. So here we can see this green color line, C and W, it will have uh, more acceleration now. And if we compare about the zones as we were discussing before, then zone 4 will be have more acceleration than zone 3. Generally, this is the concept, like zone 4 has more acceleration or more values than zone 3. So we'll go to the next slide. For acceleration, all the comparisons are here. We will discuss later on. And finally, for the model participation, if we talk about the time period, again, we can see like because of stiff behavior, less displacement, corner wall has very very less time period as compared to core wall being a flexible or less stiff system, it is showing more time period 1.53, and edge wall is almost behaving intermediate between these two. And most critical thing for the core wall is like it is showing the mode shape as a torsional behavior moment, and while the other CNW and EW is showing linear in one direction. So these are all the values from the software for the time period, calculation, model participation, mass ratio, and then we will go for the discussion. As we discussed already, we will discuss this one, like the seismic analysis of three structures as we discussed, core wall, corner wall, and edge wall. Clear difference, they show clear difference in seismic performance. Response was compared as we discussed already for diaphragm, displacement, overturning, story stiffness, acceleration, dynamic properties. And optimum configuration depends on both performance target and seismic zone. Obviously, it was changed by the seismic zone every time. Now, one by one key findings we can discuss, like center of mass displacement, as we discussed already for the corner wall, give the lowest lateral displacement in all seismic zones, zone 3 and zone 4, and also the load cases EQ and RS. Edge shear wall shows the highest top story displacement, and core wall provides intermediate in this case. So as if we write the ranking from best to worst, it will be firstly corner shear wall, then core wall, and then edge wall. And maximum displacement occurs at the roof level. For all the cases, almost it is the same case, like maximum displacement is at the top level because of the cantilever arrangement, and decrease towards the base. Corner wall offers the best resistance to torsional effects, and the CW and EW core wall and edge wall exhibit greater torsional coupling, especially under response spectrum analysis. Zone 4 produces, as we discussed already, higher displacements than Zone 3 due to stronger seismic forces, and response spectrum analysis generally predict higher torsional effects also than equivalent static. That is why we are comparing both the analysis method, and RS will be the most efficient one in calculating the actual response of the building. So in conclusion, for this typical displacement type, we can say like CNW configuration is the optimum shear wall arrangement for minimizing lateral and torsional displacement under seismic loading. Then we can talk about the base overturning movements. It will be reverse, obviously. Like the results show as an inverse relationship between lateral displacement and base overturning movements. So corner shear wall CNW being the stiffest system with the minimum displacement, and ultimately it will give the high base overturning moment and also the high base shear. So the core wall, the most flexible system, as we discussed earlier, experiences the lowest overturning moment. Edge shear wall shows the intermediate overturning moment demand between core wall and corner wall. So in performance ranking, we can say like from lowest to highest. Firstly, the core wall is the lowest, then intermediate edge wall, and then the best one is corner shear wall. So stiffer system attracts higher seismic forces, as we discussed already. The corner shear wall was the more stiffer. That is why it is attracting more seismic forces, resulting in increased base moments. Maximum overturning moments consistently occur at the base of the structure. Zone 4 produces obviously higher turning moments compared to Zone 3 due to stronger seismic loading, and response spectrum analysis generally, as we discussed already, is predicting higher overturning moments than equivalent static analysis due to higher mode. So for the conclusion of this topic, we can say like CNW configuration attracts the highest base overturning moments due to its high stiffness, while core wall attracts the least. This confirms that stiffer systems resist deformation but attract greater seismic force demand at the base. So in this category, like for the designers, if they are going to design, they must consider the more uh, forces and movements at the base of the building. Now, if we talk about the stiffness, as we discussed already, corner wall has more stiffness and already discussed in the charts before. So story stiffness shows a consistent trend across all building heights and both principal axes. Corner shear wall configuration provides the highest lateral stiffness for all the story levels, and core wall is the lowest stiffness, as already discussed. So edge shear wall system shows intermediate. In all the cases, almost edge shear wall is showing almost intermediate values. In the last, I will show one comparison table also, which will illustrate all the previous discussion and will be easy for us to understand. So stiffness ranking in this case from highest to lowest will be corner wall will be the highest, will have highest stiffness, then the edge wall, and then the core wall. So story stiffness decreases with increasing height. Obviously, this is the cantilever portion. So like this for all the configurations, indicating typical structural flexibility at upper floors. CNW is most effective in resisting lateral distortion due to its superior stiffness, and the stiffness distribution remains relatively balanced along principal X and Y axis for all configurations. So in all X and Y direction, it was almost balanced. So for our symmetric building, there was no big problem or big value difference for this one. So in conclusion of this one, CNW configuration delivers the highest story stiffness across all levels, ensuring better lateral resistance, while core wall shows the lowest stiffness, as we discussed already. And edge wall performance is almost intermediate between these two, and this should be evaluated later in all the combinations if required. Then story acceleration. Story acceleration for a good analysis or a design of a building should be less actually, and in our case, the corner shear wall is giving less acceleration. We will see the points one by one to strengthen our idea. So story acceleration and the response spectrum loading are distributed inertially along the building height. Corner shear wall configuration shows the highest story acceleration because of its less diaphragm movement. So it has more acceleration, especially at the roof level. Core wall configuration results in the lower top story acceleration because core wall is a flexible system compared to other two systems. So that is why it is showing as you can say damp resistance. It is showing very low acceleration. And for the H shear wall configuration, produce intermediate acceleration values between CW and EW. So if we mark acceleration ranking, so the lowest one will be for core wall, then intermediate will be edge wall, and the maximum acceleration will be for corner wall. The trend aligns with stiffness behavior. Stiffer systems transmit higher acceleration, as we discussed already. Corner wall is providing less movement, more stiff, so that is why it is attracting higher accelerations at floor levels due to reduced flexibility. Acceleration variation is a non-linear along height. Along the height, it is behaving as a non-linear with localized peaks influenced by model effects as in RS model, and zone 4 consistently shows as usual higher acceleration compared to zone 3 due to stronger seismic intensity. So for conclusion of this one, CNW configuration experiences the highest story acceleration due to its high stiffness, and on the other hand CW, and on the other hand the results confirm that the stiffer systems transmit greater inertial response to upper floors under seismic loading. So model analysis, finally the model analysis provide insight into the fundamental dynamic behavior of the structure under seismic loading. It is comparing the models, their time periods. So we can say that CNW configuration has the shortest time period because it is the more highest and have highest frequency because it is the most stiff structure in our comparison. And then the core wall has the longest time period because of its flexibility. H shear wall is again behaving as an intermediate, and ranking we can say from shortest to longest CNW, EW, and CW. So core wall system fundamental mode is primarily torsional because it is not very stiff. So it is, as we discussed in the previous table also, it is showing us not the linear behavior, torsional behavior actually, indicating higher susceptibility to twisting. So in this case, core wall will be more susceptible to twisting, but while CNW and EW is giving the translational in y direction linear mode. Model mass participation confirmed that translational modes dominate earlier in CNW and EW system, while CW is governed by torsional response. The distribution of model contributions explain the difference observed in. So all these are giving us difference in displacement, stiffness, movement, acceleration, behavior. So in conclusion of this one, corner wall exhibits the most rigid dynamic behavior with the shortest time period and the translational dominance, while core wall is the torsional fundamental and longest period because it is flexible. So in conclusion, we can say corner wall configuration demonstrates the best overall performance in controlling lateral displacement. Here are the values as from the model analysis. Like in the 10th story, CNW is showing 0.12 feet in both x and y direction, which is lower than the core wall, which is showing 0.15, 4 and 0.153. Performance consistency, the corner wall shows the lowest displacement again across all the seismic cases and load cases. Maximum displacement consistency occur at the top story as we discussed already, and then displacement increases with height for all the systems, and corner wall shows superior transitional rigidity because of its rigid characteristics and lower out of plane displacement on a response spectrum analysis. These are the values which we have taken from the model, and zone 4, as we discussed already, produce higher displacement. So for this conclusion, CNW configuration is the most effective system for minimizing lateral and torsional displacements than CW and EW. So for the overturning also, key findings are as it is inversely relationship is observed between displacement and base overturning moment. So these are the values as we can see for CNW has less displacement and the maximum moment. Here we can see the maximum moment. So in the moment ranking is like this: CW, edge wall, and a corner wall. So corner wall attracts higher seismic base forces due to its higher stiffness and rigidity. And the story stiffness also is same. Like for the corner wall, we can see like corner wall story stiffness is maximum in X and Y direction than the other two. So story stiffness also uh, TW is less than EW and CW is the maximum one. So corner wall remains the stiffest system even at the upper stories. Like as we discussed, a consistent decrease in stiffness with highs because of cantilever acting as a cantilever. So overall interpretation like CNW configuration consistently exhibit the highest stiffness and attracts the largest base overturning shear and movements also, while core wall has uh, totally different reaction in this one. So as a model analysis and story acceleration, as we can see, like corner shear wall will have maximum acceleration as we discussed already, and core wall will have the least one because of its flexibility than the other two systems. So this behavior is critical for the design of non-structural components and equipment sensitivity. In the model analysis at the time period, like we discuss already for the core wall, because of flexible system has the maximum time period, and corner wall because of more stiffness has the least time period. So like these are the values we taken from which strengthen over all the discussion before. So model participation results confirm that the core wall is governed by torsional dominance response, and CNW and EW are governed by translational motion in y direction, as we discussed already. So overall, as we discussed, like CNW, corner wall exhibits the higher stiffness, shortest time period, and highest acceleration, while core wall shows the opposite behavior with greater flexibility, torsional dominance. This confirms the consistent correlation between, so both are like behaving in inversely proportional. So consistent correlation between stiffness, dynamic response, and seismic demand across all configurations. So overall conclusion, as we discussed already, CNW corner wall, shear wall will be the best configuration, best performance in controlling lateral displacement and torsional response. It provides the highest overall stiffness, hence increased stiffness lead to higher story shear demands. This because if the stiffness will be more, high story demand or high overturning moment and increased story acceleration will be faced, and core wall configuration will be the most flexible system dynamically. So as we discussed already, like core wall will attract low seismic forces and is less effective in controlling lateral and torsional displacement. Edge wall will be the intermediate. So overall, we discuss everything. So final interpretation will be the selection of an optimum shear wall configuration depends on the trade-off between, like we need to select for which critical item we are analyzing our building against stiffness or force demand or displacement. Therefore, design decisions must be carefully considered seismic performance objectives and structural safety requirements and relevant codal provisions for the application seismic zones. So these are the recommendations. Preference for corner shear wall. This is the preferred. As we discussed, it is performing as a best uh, system in between these three. Corner shear wall configuration should be preferred in projects where lateral displacement control and story drift limitations are critical design requirements. So CNW system, corner wall system consistently demonstrate superior performance in reducing overall building sway and improving torsional stability under seismic loading. If we consider the design consideration for higher force demand in corner wall, obviously at the base, it is showing approximately like 22% higher than corner wall because of more stresses, and that components should be designed with more care for the foundation, for the links and everything. And the higher story accelerations are, as we discussed, it is higher. So approximately 68 inch per meter square under zone 4 in RSX as the top stories is shown for corner wall system. And torsional behavior, because this was the critical in core wall. So we can discuss the torsional behavior in core wall configuration must be carefully evaluated during design as a fundamental torsional mode like time period. So as we discussed already, it is 1.531 and in the Z direction 0.804 indicates significant twisting behavior. So core wall systems are adopted. Torsion resistant design strategies must be incorporated. Otherwise, these systems are showing a flexible behavior. Evaluation of edge wall, as we discussed already, is showing almost the intermediate behavior in between these two. So for that kind of approach, this should be checked again, do the analysis again, considering all the different soil types, structure behavior, uniformity, and everything. So basically, our focus in the design was on the corner wall and the core wall, because edge wall is almost showing intermediate behavior. So it should be, for the recommendation of research, it should be re-evaluated actually. Evaluation of interstory drift ratios for all the configurations to access localized deformed behavior. Detailed investigation of torsional movements and stress distribution within shear wall system. For this system, we should reevaluate implementation of non-linear time history analysis. For the actual earthquake values should be used using multiple ground motion records to validate and refine RSA results. Study of performance variation with different building heights, aspect ratios. Like in different conditions, it should be reevaluated. Actually, this is like a recommendation for future research for specifically for edge wall. So conducting a cost benefit analysis to evaluate economic efficiency versus seismic performance for each configuration. So overall comparison for all the types which we discussed already, like displacement. So our best is corner wall, stiffness, corner wall. Then because of high displacement and stiffness, overturning, it is more overturning moment for the corner wall, more acceleration for the corner wall, and finally for the dynamic behavior, uh, corner wall has least torsion. So this is the final comparison and conclusion for our research. These are all the references for the thesis or presentation we have taken. Thank you so very much.